Hello everyone and welcome to Immutable, a Twitch and also importantly a YouTube show where we try to learn from first principles how to build a modern distributed database. Okay, so let's get straight down to the source code. And as usual, we start with a short recap of where we've ended last week. So the general arc is that we are looking at the path that the data makes through the database. So client sends a request, that request gets converted to a prepare, that prepare then goes through the consensus implementation, gets assigned a sequence number, and then we go and actually execute that prepare, which goes through the state machine, which applies business logic of double entry accounting. But more importantly, after that, the data somehow needs to end up on disk. And that's exactly what we've been discussing for the past few episodes. In particular, last time we looked at the objects cache. So in addition to data, which is durably stored on disk, we also have an in-memory cache of objects. And when you apply business rules to your objects, you of course want your cache to be consistent with the actual state of objects on disk. And last time we looked at how exactly this cache is implemented. The two interesting features there was support for stash and support for scopes. So the stash thing is needed because the cache is also playing the role of a storage for all the objects that could be touched by a particular batch of transfers. Because remember, Immutable never ever does a single thing in isolation. It always does a bunch of things. In particular, when it processes transactions, it processes 8,000 transfers at the same time. And to make it fast, the rule is that while you are in the middle of processing those 8,000 transfers, you are not allowed to go and read any data from disk because that could potentially be slow. So you are required to read all the data that you potentially need before starting transaction. And that data that 16,000 accounts, because each transfer touches 2 accounts, that 16,000 of accounts need to live somewhere, and object cache is that thing. But because it is a cache, there is also a risk that you insert something in the cache and then an old object falls from the cache, which would be bad if you still need this object to process batch of transactions. So besides the cache, we also hold a smaller stash, which caches all the overflow, which guarantees that the objects stay in the cache. And after we have processed this batch of transactions, we can actually clear the stash because we know that, hey, we no longer need to guarantee that those objects are present. So that's the first interesting peculiarity about object cache. The second interesting peculiarity about object cache is the support for scopes. So one of our features of our state machine are so-called link transfers. You could submit 10 different transfers and you mark them as a part of the same link chain with the semantics that if any of the transfers in this link chain fails, then all of them fail. Otherwise, if any one of them succeeds, then the entire chain succeeds. The way this is implemented is that we just try executing the chain as we go, and if we hit a transfer which wasn't a success, then we roll back the last few operations. To support this feature, Object Cache maintains an undo log. So when we decide then it is time to undo our abortive chain, then we go through our undo log in reverse order and apply operations, apply compensation operations to get into the original state. Okay, so that was an object cache. Today we are going to talk about memory table, in particular immutable table and mutable table. Okay, so we are back to Excalibur. We are back to drawing diagrams. Okay, so LSM tree. LSM tree is a bunch of layers. So layer 1, layer 2, layer 3, and let's say layer 4. I think for Target we have 6 layers. Okay, each layer can contain data. So I don't know, let's say this says that full is equal to 92. This one says that like bar is equal to 2. And this one says that like bar is equal to 70. The rule is that you process the layers from top to bottom in order. So if you are looking for the value for the key bar, then you go to the first level, see that there is no bar there, and then proceed to the second level. In the second level, you get the value for the bar key equal to, and you return this value. And you never ever go to get to the level number 3 because level number 2 contains the answer. And all those layers are physically represented as tables on disk. The question is, so kind of like let's maybe draw a little bit of tables here. So kind of like those things are like tables. Let's say like 3 tables on the first level, 2 tables on the second level, like, and well, a couple of more tables on the last level. Okay, so that's disk. How do we get the data on disk? And the overall rule here is no. I want to select the entirety of this thing, including the layers. Okay, this is better. The rule, as with everything in Target is that we never ever going to do a single thing at a time. So, okay, let's say that a new operation comes in from the user, and we say that like want to say that bar now equals 42. Oh, 52. Okay. So how do we deal with this new operation? again, kind of like we could immediately go and like write it to some new table for level 0, but that is like kind of like wasteful because we have only a single key and value. So what we actually are going to do here is that in memory, so let's do a bright dividing line here, and let's say that this line, disk, below this line we have a disk, and above this line we have random access memory. Okay, so the rule is that we are actually going to keep the data in memory and accumulate. How can we? Yeah. Yeah, and we are going to accumulate a whole bunch of new values in memory and group them in a table. And only when the table is full, only when it contains a lot of values, then we are going to move this table to disk. So that is kind of like the rule. And the question is just how many values do we need to group to move data down? And the answer is that is exactly that LSM batch multiple, the most horribly named constant in the entirety of Immutable, which I've been complaining about. So let's take a look at it. In constants, we have LSM batch multiple. Yeah, and that is a parameter of our cluster. And that is 32. So going back to our picture here, and let me reset for while it was in memory. Okay, so each batch is 8,000 transfers. We accumulate 32 batches, so that is going to be 8,000 times 32, which is, I think, about 500,000 transfers. So we accumulate 500,000 transfers, and we store information about all these transfers in in-memory table. After 500,000 transfers, we take this table and move this table to disk in one go. Now, there is extra thing, because like moving table to disk actually isn't an atomic operation. It takes some time to process this data to physically move this. And while we are moving this in-memory table to disk, we actually would like to continue processing new transactions. So what is happening here is that we have two tables in memory. So one is mutable. Okay, I'm very horrible at handwriting, but I will try. So this one is mutable, and this one is immutable. Now, what happens is that table immutable was just mutable table. When we accept new operations, we are going to just append them to the mutable table as we go. And sorry, I didn't want to do this. Okay, so after the immutable table is fully full, what we are going to do is that we are going to swap the buffers. So we are going to say that, okay, now table mutable is actually this new table, which was formerly empty, and table immutable is this thing. So after we did the swap, actually we can spend another LSM Bash multiple prepares appended to the table immutable, which is now empty. And while we are appending there, so let's say that we appended something new here. I'm running out of letters, so let's say it's going to be x equal 10. While we're appending x equal 10, what we are going to do with this thing is that we are going to copy it on disk. And after we have copied it, we can say, okay, that data is now on disk, so we no longer need table mutable, so it is free again. And by that time, probably this thing is going to be full. So at this point, we flip the pointers again and continue this process. So that is the setup for table mutable and table immutable. And important note, let's say that we are in the middle of this update. So in kind of like in the middle of the things, you have table mutable with like the freshest data, which is currently being appended. Then table immutable, this is a complete table which is going to end up on disk soon, but it is in the process of being written to disk. And then you have like stuff on disk. So if at this point someone comes to you with a request, you should process them in this order. Okay, so I need a free-form error here. So you should start with table immutable, then you go for table immutable, and then you go through all the layers. So this is the path of LSM tree. So for example, if someone asks us, hey, what is the value of key Z, then we say, hey, Z is 9 because it is stored in table immutable. If someone asks us about kx, we say, hey, x is 10 because it is an immutable table. If someone asks us about key bar, then we go to the first 0th level of LSM tree and look it up there. So that is general setup. Let's look how it is implemented. And accounts. What do we do with accounts? Accounts update. Yeah. So that is the entry point. The code of a state machine, which implements a single transfer from account A to account B, which updates two accounts. Again, reminder, why we are passing both the new account and the old account to the update method. That is because we also want to update indexes. So one account object physically is represented as a bunch of different LSM tree. There is object tree, which stores accounts themselves, sorted by their timestamp. Then there is ID tree, which stores account timestamps keyed by account ID supplied by the user, and then there are indexes for various fields of account. Okay, so if we go into this update method, that's going to be growth update, where we do this indexing update, where we make use of both old and the new field. Then we put the object into our objects cache, something that we have looked at last time. And finally, we go and insert this into the object tree. So again, this is super simple, just as I have explained. We insert object. Where should we insert? Well, there is only one place where we could insert new data, that is table Mutable. So we insert it there. So what is table Mutable? Well, it's table memory, and it is super simple. It is just a slice of values. And value count limit shouldn't be, I mean, we don't need our value count limit, because value count limit is exactly values len always, I think. The only thing which stops me from just going and refactoring this is that I also have at least deja vu that I already did this and that didn't work for some reason. But okay, I need to revisit this anyway. Oh, actually, I think this just must be fixed on the main branch. So let's actually refresh our source code. Okay, yeah, okay. Hey. Value count max is gone. So that's for a case where deja vu was actually a real memory. Okay, so table memory. Table memory is just a slice of values and a bunch of extra things, which we'll look at a little bit later. But for example, the put, like how do we add a new value into table Immutable? Well, it's pretty simple. We just write it into a values array, and then we increment the count of values that we have. Now, the question is like, so we just, like, we just append values, like store them in an array. Very simple, very straightforward. The question, like, what is like the value context and why this isn't just value count? Well, this has to deal with scopes, because table, like table memory, table Mutable, like object cache, has to support the scopes API. And scopes, where is like scope open? Okay, scope open I think should be on the tree level. Scope open. Okay, so when we open the scope, we store this value context. And then we close scope if we want to discard data. So we want to roll back a bunch of transfers because one of the transfers in a link chain failed. We just go and restore the old context. And that means that we essentially just forget about those few most recent values which we have inserted into our table. Okay, so that is super simple. Okay, so what do we do else with our tables? Okay, yeah. Okay, here is a bug in Z language server, Zik language server. You see, like there is like highlighting is like completely wrong. Like this index field helper type is highlighted like in the middle. So there is like some word tearing, and that means that there is like some pretty serious bug in ZLS where it could get into inconsistent state where you switch branches, and that is, yeah, that's generally not good. But we can always just reload window, and that will fix us any data. Okay, yeah, now it's much better. And we want to look at update. Okay, we just call put, and that calls put in. Okay. Well, I guess, yeah, I guess let's then, well, before we go and look at the rest of the table memory API, one like very useful thing to understand the physics of a database and to understand how trackability is like allocates of memory is to trace like how we size this table memory, because okay, this is just an array of values, and of course if we just add in and add in and add in values there, it might overflow. So we somehow need to make sure that we don't add too many values. So how do we do this? Well, you see, we allocate value count limit items for our table. So how is this value count limit determined? Well, table, well, actually, I haven't shown you where table is stored, and this is it. So table immutable is just a field of a tree. So when we initialize this tree, we pass this value count limit, and value count limit we compute as batch value count limit times number of batches in our compaction interval. So that LSM batch multiple, that 32 prepares. So a single prepare can create this many objects, and then we take this many prepares before we flash data to disk. Okay, so let's take a look at the rest of the API. So I guess the interesting part is make mutable. So where we do this like pointer swap, where we say, okay, so now old table immutable is the new table mutable, and the old table mutable is the new table immutable. This is make mutable function. And this is where we do this. So we swap mutable and immutable. We say that mutable table is now immutable, and table immutable is now mutable. Make mutable is very simple. We go and we just like zero out everything. Make immutable is slightly more complicated because we need to sort the table first. And why do we need to sort the table? Well, because all tables on disk are sorted so that you can binary search it. We cannot easily keep table mutable sorted because remember, table mutable stores values in the order which they were appended, which might not necessarily match the sorted order. But once we change table mutable to table immutable, at that point, we actually know that, hey, our table isn't going to get mutated. Well, it's immutable. So we can safely sort it at that point and be sure that, hey, sorting actually cannot break afterwards. So that is another thing which we do when we do this buffer swap. Okay. And I guess there is one extra thing. Like how do we do lookups? Because remember, I kind of like, yeah, I guess I think I kind of like lied to you. I kind of like said to you that like when we do a lookup, we first go to the mutable table, then to immutable table, then to levels on disk. And that kind of like doesn't really work because, well, what is a lookup? Lookup is binary search. So, and we can binary search table immutable, and we can binary search layers on disk because data there is sorted. But for our mutable table, the data is stored in the arrival order. We cannot binary search it. We could do a linear scan there, but that is going to be super slow. So what do we do? And the answer here is this. Things in the mutable table were added very recently in the latest LSM batch multiple of prepares. And oh dear, I now understand a question I had 2 episodes ago. And we have an invariant that these objects are still there in our object cache. So remember, before everything, like before we even get to the layers, there is this object cache. And it is an invariant of object cache that it is actually, okay, it's going to be super awkward, but let me try to explain this. Okay, yeah, perfect. So there is an invariant that object cache is a superset of a table mutable. And object cache internally is essentially a hash table. So while logically we do a lookup through table mutable, physically that lookup happens through the object cache. And actually, let me just verify this real quick that we are not missing this. And also to like remind you how lookups are done. Again, what we want to look is not the execute we don't want to look at the create transfer because yes, we do look up objects here using get, but this lookup only goes to the cache. So if we look here, you see like this get like goes strictly to the cache because the contract here is that before we get to create transfer, we run prefetch so that all objects that might have been needed to be fetched from the cache actually end up in the cache. What we are interested in here is prefetch. Create prefetch. And the method we're interested in is prefetching queue. And let's quickly go through this prefetch loop. So we are trying to prefetch object. And if this object is an object cache, then we return it. Otherwise, we go and try to prefetch from memory, and we do lookup from levels. And you see, when we do lookup from levels, we do lookup in table immutable, and we don't do lookup in levels. So like potentially what we could do here is we could say if constants verify, then for 3 table mutable values, value assert do we have like key from value? Okay, well, I don't remember where key from value function is in this context here, but basically want to say this. We want to say that whenever we look up something from levels, then the data cannot be in table immutable because it must be in object cache. But we don't do this because, well, this actually the case where this is a too hot of the assertion even for constants verify, because this is data path. So this is the place where we don't do batching. This is where we run one for every transfer and not once for every batch, or once for, let's say, batch multiple batches. And this is the case where we change complexity from logarithmic or constant time to linear. So that's too much of a slowdown. Okay. But I think what we actually could do, I think. I think here we actually could go and assert that object cache contains all of the objects here. Well, maybe this is actually done at the call side. Let's take a look. Who calls this function? Forest calls this. Forest doesn't really have access to the groove. Okay, this is okay. This is deep in the guts of compaction, and we'll get to compaction at some point. Well, actually very soon, but I'm probably not too ready to do this. Yeah, but yeah. So basically here I want to do something like, well, actually, okay. Let me do this. So the moment where we swap table mutable at table immutable is actually the same where we update our cache map. So let's see where that happens. Object cache, objects cache, compact. Okay. Groove type compact, and well, okay. Who compacts the groove? Forest well, it should be forest. Forest, how do you do compaction? Okay. Okay, I'm not quite ready to, well, one more try. Let's start from replica. So replica calls state machine compact. So compact is like exactly that point where like this mutable immutable flip happens, where object cache, where we drop the stash in the object cache, and where we start writing data to disk. So no, okay. I don't see who compacts the groove, and the moment where we compact the groove is actually where we should be. Okay, I know how to find this. Okay, let's go to groove. It has compact, and let's say that like there is no such method, and then we try to compile the code, and we'll see hopefully the call site. Although I've recently rebased code, so it might take some more time to. Okay, I rebased code so fiercely, then I actually need to update my version of Zig, because that is still like zig 0.11, which is not what we need here. Okay, music. Then we try to build the thing, and it will say who compacts the growth. Okay, yeah. Well, now you see why, like, grepping for like growth.compact doesn't yeah, didn't actually I didn't actually show this thing because, well, yeah, kind of like meta programming makes everything hard. Like avoid meta programming if you can, but in this case we actually sadly cannot. Okay, so we do this. They do this in compact callback, and okay. Okay, so yeah, probably in the Groves compact call, we should be able to do this assert that, hey, kind of like everything that's in object cache is now going to be in table immutable. Okay, so what does this leave us with? Well, let's remember where we were. Okay, table. We were in the table memory. And I think we actually kind of like, basically discussed most of this. So put is trivial, get is trivial, make mutable is trivial, make mutable is not trivial because we need to sort. And yeah, and that's basically it. Well, one extra thing here is that for scans, sometimes we actually might want to sort table mutable as well, which we'll get to once we get to the scans. So that's why kind of like, what we actually do is that we lazily sort values. So we remember if the values are sorted, and if they are sorted and we insert a new value which breaks the sort, then we kind of like say that it is sorted only if actually the newly added key doesn't break the sort. Okay, and that is kind of like embarrassingly little time. And that means that I spent embarrassingly little time discussing this because, well, this is actually way simpler than object cache. And that means that probably I need to start talking about compaction. So we kind of like, we understand this like general, hey, like every 32 LSM batch multiples, we are going to run this compaction thing, but we like haven't looked at how this all ticks. And for that, well, let's go to replica because this all is driven by the replica, I think. So in the commit op, we ask the state machine, ask the state machine to commit. After state machine commits, somewhere we should say, hey, compact this op. State machine compact. Okay. So after we commit the op, well, let's see where we commit the op. So we commit the op. And afterwards, we do commit dispatch. And in the commit dispatch, we do compact state machine. Okay. And then we go to the state machine. And we run this compact. So kind of like this is like slightly tricky. Compaction, like compact doesn't actually, like, run the entire compaction from beginning to the end. Rather, it is kind of like says, hey, this is the next op. So kind of like if you like, basically it's kind of like, just periodically checks it with this compaction process. It says, hey, kind of like this is the op we are looking at, and like if you would like to do something with this op, then like please do this. So there we call forest compact. Okay, and probably for this function we could spend a little time. And maybe not. Well, what is happening here? So we say progress. Oh, okay, yeah. We say bit, and then we get like into like the guts of compaction, which I absolutely have no desire to stare at today. You have to wait for the next week for that. Okay, then okay, then let's just say, okay, usually, like I usually tend to finish later, like, an hour and a half, like 2 hours. Well, probably we didn't have 2 hours, but like, well, maybe we could. So let's say that today is going to be a nice short episode, so you could be lucky that you have extra 30 minutes of your life clawed back from evil Matclat, which tries to steal an hour of your time every Friday. So let's then do a recap, and the recap is basically this picture. So we have a standard LSM structure on disk, but above this disk we have some data with RAM. And data with RAM is really simple. It is prepared in exactly the same shape as we're going to write it on disk, as a table that is a sorted array of values. And the idea here is that when the new data comes in, we fill in memory table. Once it is full, we go and shovel that to disk. One tricky complication there, or rather like not complication but optimization, is that writing table to disk takes time. And while we are doing this, it would be cool if we could actually proceed with accepting new data. And that is actually easy to do. We could set up a double buffering setup where we actually have two in-memory tables, and while we are writing one table to disk, which needs to be immutable because we are writing it, we append new data to the second table. Once the first table is flashed, we go and we swap the buffers there. And to make everything deterministic, rather what we do is not like, hey, once the table is flashed, let's swap the buffers, but we rather say, okay, table has to be flashed by the next multiple of 32 prepares. And at that point, we swap them. So kind of like there is like fixed points where we do this buffer swap, and we optimistically hope that OIO happens before that, but if it doesn't, at that point, we are going to block. Okay, and then we do like hierarchical lookups. Now, the second part of the fact that the data in memory mirrors data on disk is that data is sorted. And that works for table immutable because, well, it is immutable, it doesn't change, we can modify it. It doesn't work for table mutable because table mutable stores values in their arrival order. The motivation for that is partially to support scopes and partially because maintaining sorting data is just costly. Again, we want to do everything batched. We don't want to like maintain sortedness for every single value. We'd rather do one single sort at the end because that's going to be faster. So we need to do something with that. And what we do with that is that we just say that table mutable is always a subset of what's in the object cache. So rather than, although logically we start working through level through table mutable, in reality we go through the object cache. And one thing I actually wanted to say is that when we initialize object cache, then we yes. This is so. This is like constant constant LSM batch multiplied is something I stumbled upon last time. So today we like understand the reason for that because we must make sure that cache is a superset of table mutable, and for that to be the case, it must store at least as many values as table mutable, and that can store an entire LSM bar of repairs. Okay, I think that's it, and see you next week for probably the most exciting episode of this entire arc about LSM, the episode where we start digging into compaction code. Please prepare a copious amount of food, of tea or coffee or other beverages, because that's going to be like super complicated, super convoluted control flow, a lot of concurrency, and like my brain is going to melt, and yours brain is probably going to melt too. So exactly 1 week minus 52 minutes from now at 5 p.m. UTC on Thursday, we'll start discussing compaction, and see you then. Goodbye.